What's up, guys? Welcome to this little R session. The purpose of today's session is to show you how to do some basic calculations for multi-step transition probability matrices, and then also how to calculate marginal distributions. Okay, now as usual, what I'll do is I'll share with you a template file, and this template file will have some tasks in, and I'll actually just walk you through the tasks, showing you how to do the calculations. Okay, now just some syntactical notes if you want to brush up on anything in case you're just not familiar with it yet. In any case, I expect you would be. But things that you might want to know how to do in R before we start is just one, matrix multiplication. Two, we're going to be using loops. And then three, we're also going to be writing functions. So yeah, if you want to, you can just go brush up on that. Otherwise, you're just welcome to follow along. So let's jump in. Okay, cool. So let's have a look at the template file. What have I given you? So I give you an arbitrary transition probability matrix. So it's a nice three-state Markov chain. And then I give you three tasks. First task is to calculate the four-step transition probability matrix from the above. Okay, so that's going to be nice and simple. We're just going to power up that matrix. Task two, calculate the marginal distributions using the following initial distributions. So delta naught equals C1 naught naught, etc. And then I'll also ask you to plot the distribution, or the probability rather, of this process being in state 2 at time points running from state 1 to 10. Okay, and we're going to alternate between those configurations of the initial distributions. Okay, so I give you some initial vectors there, and we'll just write the code after that. Okay, task 3. Write an R function which calculates the marginal at t for a given delta naught and gamma. And then calculate delta 4 and compare that to a four-step transition probability matrix for delta naught equals C1 naught naught. Okay, so we're presumably going to be reusing some of the calculations. Okay, then just to reiterate again, this first line, these are just going to be some graphical parameters that I set, sort of make the plots that are going to pop up nice. Second line, rm list equals ls, that just flushes the workspace. Okay, cool, so let's kick off. Given an arbitrary transition probability matrix, okay, so let's just run that and check what gamma looks like. Ooh. There you go. Okay, so I did typeset correctly. Nice, okay, nice and simple chain. And we are tasked with calculating the four-step transition probability matrix. Okay, so how are we going to do that? So again, by way of the Chapman-Kolmogorov equations, what we know is that we can, for example, calculate the two-step transition probability matrix by simply post-multiplying the one-step transition probability matrix by itself. Okay, so that's nice and simple. In R, we just use the matrix multiplication operator, and we can get out our answer. Okay, now we can do the same thing for three steps. So just continue on multiplying those matrices, and that essentially just powers up the matrix. Okay, and then we'll get the four-step transition probability matrix. Okay, so that was nice and simple. Okay, now this usually takes a bit longer when you're doing things by hand, but you can now use R to check your calculations for simple matrices like this, and maybe larger ones as well. Okay, task 2, calculate the marginal distributions using the following initial distributions. Okay, so I give you an initial distribution. First thing we need to figure out is how to calculate, I guess, delta t for general t, so that we can just iterate through it. Okay, now, how do we do that? Well, at the initial point in time, which is t naught, we'll know that, okay, we're just going to denote it delta underscore t. Okay, and we're going to say that at the initial point, that's just going to be equal to whatever delta naught is. Okay, and we'll start out with this first one I've given you. Delta naught equals C1 naught naught. Okay, so what does this actually mean? So this means that at the initial point in time, so t equals naught, state 1 is occupied with certainty. So remember, this vector is a distribution across all the states of the process. And what it says is, well, you're in that probability, or you're in state 1 with probability 1, and all the other states with probability 0. Okay, so let's just look at that one first. So delta t equals delta naught. Okay. Then for longer time horizons, okay, so what we want to do is we want to calculate this delta t maybe one step later. Okay, so delta t plus 1, how do we do that calculation? Well, we say whatever delta t is going to be, has to be transpose, okay, and I'll explain that in a second, transpose of whatever it was at the previous time step. Okay, now remember we've set delta t equals to delta naught, so the previous time step was naught. Okay, so we're calculating at time step 1 now. Okay, so we just go transpose delta t, and then we post multiply by gamma. Okay, so the transition probability matrix. Okay, now remember what our equation looked like. We said sort of delta s plus 1 transpose equals delta s transpose post multiplied by gamma. So because R stores things in column vectors, well, this thing chucks out a row vector, and what we want to do is sort of make that a column vector again. Okay, so we're just going to transpose that calculation so that we get the correct thing out. Okay, so let's see if that calculation works. Okay, let's just run everything after that. So run all the comments, run past that, and delta t equals delta naught, so that initializes, and then we'll do one step. Okay, so what does delta t look like now? Okay, 0.5, 0.5, 0.5. Okay, so does that make sense? Let's just quickly check gamma. So if you're starting in one step later, yes, that makes sense. So that should look like this row, right? So why is that? Well, the first element's 1 here. That's just going to return the row there. Okay, cool. So what about longer transition horizons? Okay, so we want to do this for t running from 1 to 10, right? Okay, so we're just going to loop that calculation, and each time it's going to calculate a new delta t and sort of advance the index once and calculate the distribution. Okay, so what's going to happen is delta t here is going to change here at every iteration. Okay, so we can maybe have it print that. Okay, so print delta t as you calculate it. Okay, so let's just sort of flush everything, run again. Unexpected for t equals. Why do I say equals? I should say in. Idiot. Anyway, let's run again. Okay, cool. So what happened? Yeah, okay, it ran through all of those calculations, and you can actually check how that vector changes. Okay, so the marginal distribution, how it changes over time. Okay, cool. So that was nice and simple. So that calculates the marginal for the first initial distribution. What was the other part of the question? Oh, we want to plot the probability that the process is in state 2 for t running from 1 to 10. Okay, so what I'm going to do is, so let's plot, let's set up the plot region. Okay, so let's go delta, so at the initial point in time first. Okay, we're going to look at delta 2, and we're going to plot that at what time point? Just C naught. What kind of plot are we drawing? Is there anything else? Okay, so we're going to say type equals P, so draw points. Okay, then we're going to have to set the X label to T, otherwise it's going to say C naught, and then our plot's not going to make sense. What are the other things we want to set? Maybe we want to set the Y limits, because we know these are going to be probabilities. We're going to set them to be 0 and 1. What else? Oh, the X limits. So X limits, we know we're going to be plotting. Okay, let's start from 0. I'm going to put the initial point there as well. From 0 to 10. Let me check, is there anything else? PCH, just use the correct plotting character. Make it 16, so that's going to give us a solid circle. And what else? Oh, we maybe want to color this in. Okay, so we're going to make it lime green. Okay, so it's going to make it nice and bright. So that's just going to set up the plot region. And then what we want to do is maybe we want to delineate some reference points in the probability level, or reference probability levels, I guess. So we're going to go AB line, and we're going to draw some horizontal lines, and we're going to draw them at 0, 0.5, and 1. Okay, and we're going to say LTY equals 2, so it's going to draw dashed lines. Nice and simple. Okay. Okay, so that's going to set up the plot region. So what I'm going to do now is, I guess I'm just going to borrow. Okay, let's just run it first. Okay, let's just plot first. It'll set the graphical parameters, and it'll drop it in. It'll draw the plot in the bottom right of in the bottom right pane. Let's run everything up to there. See if it does it. Okay, cool. So what have I done here? I've set up our plot region. You can see the initial point here. Okay, so the probability of being in state 2 at step 0. Okay, yeah, that makes sense. It's not. Okay, so it's drawn it there. I've got our reference lines going here. We're looking at delta t, the second element in that vector. Okay, so that's on the y-axis, and then on the x-axis, we just have time. Okay, and now what we're going to do is we're going to keep adding to this plot. So every time we calculate the marginal distribution, we're going to look at the second element and put that on this plot. Okay, so how do we do that? Well, we're going to use, we do the calculation. So we already have the vector. So we then go points. And then we're essentially going to do the same thing. Okay, so we're just going to copy from here. So I'm going to say take delta t, take the second element, and plot that at, okay, yeah, so that gives you the y coordinate, and plot that at what point? At t in the x axis. Okay, and again, what we want is the correct plotting character. So make that 16, so it draws a solid circle. And then we're going to say color is going to be lime green. Okay. So it's going to keep adding to that plot. And what I want to do is I'm just going to say sys.sleep and sleep for 1 second. So what that's going to do is that's just going to interrupt everything for 1 second. So it's just going to pause it, plot, pause, plot, and so on. Okay, so that'll just make the visualization a bit better. Right. Okay, and that's going to plot everything. So I guess what I want to do now, I guess I'll run the plot and then I'll have it, I'll use the Windows trick to actually pop it up. Okay, so let's run everything. Okay, so it's adding to our plot, and what do we see? Okay, we see how the distribution changes over time. Okay, or I guess that probability. Okay, so let's see if that probability makes sense. Okay, so starting at time 0, state 1 is occupied with certainty, so it's definitely not in state 2. So the probability of being in state 2 is not. That makes sense. 1 step later, the probability of being in state 2, oh, that's going to be 0.5. We know that. We can read that off from the transition probability matrix. Okay. Well, 1 step up from there. Okay, well, let's look at the second calculation of the marginal. And what do we see? Okay, it's going to be 0.375. So that's round about there. And then subsequently 0.2187 and so on. Okay, and then it'll vary like that. Okay, cool. So that's interesting. That's for the initial distribution C1 naught naught. Okay, simple enough. So let's just rerun that. But now for a new delta naught. Okay, so I'm going to comment out the first delta naught and let's look at the second delta naught. Okay, so what does this mean? So for this initial distribution, well, at time 0, state 1 is occupied with probability 0.5, or state 2 is occupied with probability 0.5. Okay, so notionally, I guess the idea here is that when you don't know what the initial state of the process is, so when you don't know what the initial state of the process is, well, then I guess you might have to assign probabilities to what states it can assume at that point in time. Hence the initial distribution, and in this case we've set the initial distribution to be probability of 0.5 being in either state 1 or state 2, and probability 0 of being in state 3. Okay, and then we can just rerun our calculation. Okay, so let's rerun our calculation. Interesting. So I guess a similar sort of pattern. Okay, now again we can check whether this makes sense. Right, so at time 0, probability of being in state 2 is 0.5. We know that. Okay, cool. So on the reference line there, yeah, we see it over there. One time step later, well, we do our little calculation and we see that as 0.375, 0.2187, and so on and so forth. Okay, cool. Right, so I guess what do we need next? Okay, so let's do task 3. Write an R function which calculates the marginal for t for a given delta naught and gamma. Calculate delta 4 and then compare that to the 4-step transition probability matrix for delta naught equals C1 naught naught. Okay. So basically we're just going to sort of rehash those calculations that we've just done. We're going to sort of wrap it in a nice little function. Okay, so let's call that function d underscore t. So d underscore t equals a function. Okay, and what parameters does this take? Well, we want to tell it what time point we want to evaluate that at. We want to give it an initial distribution, so a delta naught and a gamma. Okay, so those are going to be the parameters of our function. And then we're going to have to do some calculations. Okay, so this function is going to have to calculate the marginal at any t. Okay, so presumably the person will give you a t run being either 0, 1, 2, etc. Okay, and it's going to have to figure out to do that. Okay, so what are the bits we're going to borrow from this previous calculation? Well, we have to initialize. Okay, so delta t equals delta naught, whatever that is. And okay, well, if the person supplies t equals naught, well, then that's just what we're going to return. Okay, so if t equals naught, okay, what do? Well, just return. Okay, and what do we want to return? A list. Okay, and this list must contain delta t, and what that must be is, well, it must be equal to delta naught. In any case, we've initialized, so we could have just said delta t equals delta t. That'll be the same thing. Okay, so that's where we're going to return a list. Okay, so let's just check if this initial bit works. Okay. Hopefully it does. So we're going to say evaluate at time 0. We're just going to borrow from before. So I'm going to comment out that and set delta naught equal to C1 naught naught, because that's going to feature in our calculation, and then I guess our comparison. Okay, so let's borrow this. So delta naught, we're going to pass that, and then we're just going to give it gamma, so whatever we have. Okay, so let's see if this calculation runs. Okay, so let's run function definition, delta naught, and let's call dt at time 0. Okay, and it just returns that vector. Okay, now at this moment it doesn't do any other calculations, so we can check that. Well, let's maybe plug in something else, and okay, cool, it doesn't do anything. That makes sense, right? So if t equals naught, do that. Well, if it's not equals to naught, so because this happens after, well, we can just do the following. Okay, so let's borrow this loop. Let's borrow the top part. Okay, so so you just want to sort of loop again through this little calculation, and okay, so I'm just going to set a new index for I running from 1 to whatever t is specified. Okay, right, so why do I specify a new index? Well, it's because our one parameter is now taking the name t. We want to evaluate up to some point t. So what we need to do is we need to iterate through this calculation t times, essentially. Okay, and we're going to calculate that delta t. Okay, at the point at which it's finally calculated, we then return what? Well, we return whatever the result of that calculation is. Again, going to return a list, and in that list, we want to return delta t, well, which is delta t at that point. Okay, so cool. What's going to happen in this function? If the person says t equals naught, it's going to return delta t, whatever it is at that, well, delta naught at that stage, and not do anything after that. Otherwise, it'll just pass over that and then run through the loop and return the calculation. Okay, cool. So what we're going to do now is we're going to say delta naught equals c1 naught naught. And the task says calculate that at time 4. Okay, so run that calculation and then compare it to the 4-step transition probability matrix. Okay, so let's run our function, and this is what it gives back. Okay, so that's the marginal distribution at time 4. Let's borrow from here. So we already calculated the 4-step transition probability matrix, and let's compare to that. Cool. Right, so what do we see? Okay, let's compare these two. Well, okay, so what do we see? That vector is just the same as the first row of the 4-step transition probability matrix. Okay, so, okay, well, that makes perfect sense, right? Because how do you calculate delta t in general? Well, if you look at our calculation, essentially what we're doing is we're saying calculate delta t as delta naught post multiplied by gamma, post multiplied by gamma, and so on and so forth. Okay, and how many times? Okay, so delta naught times the t-step transition probability matrix, where t is now going to be whatever. Right, so in this case, it's going to be 4. Okay, and because delta naught is just c1 naught naught, that means return that first row. Okay, so we check and I'll see that our calculation makes sense. Okay, so essentially what you can see here is that we can actually use the marginal distribution calculation to return rows on the t-step transition probability matrix. Okay, so this is a nice general way to actually calculate transition probabilities, not just the marginal distributions. Okay. Right. So I guess that's that. I'll check you in the next one.